Welcome to Sustainable Solutions. I'm Chloe, and in this series, I chat with leaders from a wide range of industries about the innovative solutions driving us towards a sustainable future. Today on Sustainable Solutions, we have Professor Greg Metha. Greg is a professor at the University of Adelaide who has spent his career working on catalysts. Now he's an innovator, having developed a novel manufacturing method for green hydrogen that has a lot of promise. In this segment, Greg has a lot to offer as he recounts his experience in research and now working with the likes of Fortescue Future Industries to migrate his work from the lab to the Australian desert. Hi Greg, thank you so much for joining us today for Sustainable Solutions. Firstly, I wanted to ask you, what is green hydrogen exactly?
Hi, Chloe. Nice to be with you. Yes, green hydrogen. Let's start with hydrogen. Hydrogen is the simplest and lightest gas that we know of. So hydrogen is first element on the periodic table. Two atoms of hydrogen come together to make molecular hydrogen, or H2. Hydrogen is used extensively around the world. It's used primarily for upgrading fossil fuels. So in chemistry terms, we talk about hydrogenation type reactions. So it adds greater value to hydrocarbons. And secondly, it's used to make ammonia. And with these two processes, it is actually made around the world, sold and consumed at massive scales. Now, where does this hydrogen come from? The vast majority of it, so over 90%, perhaps more like 95% of it, is made from natural gas, from methane. So methane has chemical formula CH4. You react the methane with actually steam, so water vapor, and then you effectively extract the hydrogen out, and that hydrogen is then used for all of these processes I mentioned before in the hydrocarbon industry and to make ammonia. Now, the downside to that is that carbon atom, because in order to extract the hydrogen, they oxidize the carbon and you make carbon dioxide. And this is exactly why we are now over 440 parts per million of CO2 in the atmosphere, and it's increasing. And this is leading to the problems with climate change. And just in the, as you're aware, in the last month, we're seeing all of these horrendous climate changes that are happening, particularly in the Northern Hemisphere. And come our turn for summer, then we're expecting things to not be very pleasant either here as well. So we use hydrogen a lot, but the way that we're making it produces and exacerbates the climate change problem. Green hydrogen is a way of making this hydrogen without the carbon or carbon dioxide footprint. So it's made through a process called electrolysis, where you apply a voltage to water and you split the H2O into hydrogen and oxygen. Now, it requires energy. So what's important is, where do you get that energy from? If you get that energy from a coal-fired power station, it's no good because you're still making CO2. But if the electricity comes from, for example, a photovoltaic farm or a wind farm, so renewable energy, or what we call green electricity, then that hydrogen is then made without that CO2 being made as well. So that's what we call green hydrogen. It's hydrogen, but it's made without that CO2 footprint. So that's the difference here. And so what people have done is they've come up with all of these different colors of the rainbow. So although hydrogen is an invisible, transparent gas, they talk about green hydrogen. We actually talk about pink hydrogen, where the hydrogen is made from electricity that's derived from nuclear energy. So not in Australia, but certainly in Europe and in the US, we talk about pink hydrogen. There's turquoise hydrogen, where the hydrogen is again made from methane, but it's not done with the typical chemical process. It's made to extract the hydrogen, and the carbon is left as solid carbon. So it doesn't make carbon dioxide, it leaves you with solid carbon. So that's turquoise. And people are getting very excited now because there's such a thing as white hydrogen or natural hydrogen. So people have now realized that just like natural gas is formed underground by these geological processes, hydrogen is now also made in these geological processes. So it's possible to mine this hydrogen, and we're not exactly sure what its carbon footprint is going to be, but it's certainly going to be less than, for example, the hydrogen made from natural gas, which I forgot to mention is called grey hydrogen. And there's black hydrogen, there's yellow hydrogen, all these different colors of hydrogen.
Wow.
And it's all got to do with how it's made and what its CO2 footprint, associated CO2 footprint is.
Okay. Do you want to continue? You continue. Go
Oh,
ahead.
I was just going to say something about cost, but I think you're going to that will come in your next question.
Okay. No, because so you've given us a bit of an insight on how like green hydrogen perhaps is typically made, but you're making, segues because you're doing it in a pretty unique way. I was hoping if you could share with us how you're doing that.
Yes. Okay. So as I mentioned before, green hydrogen is made by applying a voltage to water. And if that electricity comes from, for example, a photovoltaic farm, then you can think about a process where we've got solar energy coming in to a photovoltaic cell. That photovoltaic cell is producing electricity, and that electricity is going into a piece of equipment called an electrolyzer, which then splits the water into H2 and O2. So I mentioned at the start photocatalysis. So this is a process whereby you don't produce the electricity. You have light coming in from the sun, and you have a very, very special chemical called a photocatalyst that directly absorbs that energy from the sun, the photons from the sun. There's water present, and you directly split that water into hydrogen and oxygen coming off as well. So you completely bypass the need for producing electricity. It just does it directly. So what this allows is potentially the cost for that process to be much, much cheaper than electrolysis. And in electrolysis, a large part of the cost is associated with purchasing the electricity. So because the electricity typically comes from the grid, where you have to pay a price for it, and that's what really makes the price of green hydrogen so much higher at the moment. And at the moment, it's about 3 to 4 times higher than the hydrogen from natural gas or grey hydrogen. So that's the problem with green hydrogen. Everything comes down to the fact that we know how to do it. It all comes down to economics. And same with photocatalysis. We are now developing systems, making them larger and larger. We're past the proof of principle stage in the lab. It's now to the point of deployment. How much can we deploy this technology at? So it's really about seeing how cheaply you can make this green hydrogen. So our technology it hasn't been given a color yet, although people typically do say it's green hydrogen because it's made from water, but it really is an emerging competitor to electrolysis, the other type of green hydrogen.
You have like your own hydrogen. That's pretty cool. Your own colored. But actually, I want to ask because you're kind of delving in a little bit to the idea of like the economics of it and the cost. And I wanted to ask because for your project, you're a professor at the University of Adelaide, so they're supporting the project, but you also have the likes of Fortescue Future Industries, who is probably, I'd say, at least here in Australia, like I think of green hydrogen, I think of them. So how has that helped you innovate or perhaps like move more quickly in this process, having the support of both of these two major institutions?
Yes, that's a good point. So, of course, universities, that's the role of academics in the university to do research. And you could do research on very fundamental things, like I mentioned before. That's what I started out doing, or you could start to have increasingly applied research. So that's the transition that I've made over the last decade, where I started to do more applied research. As we started to come up with these ideas, we're developing novel ideas, and we realized, hey, here's something that nobody's ever done before. It potentially will have a huge impact. So I go to my university and I say, here's something that could be worth a lot of money in the future. And the universities nowadays are thinking about commercialization opportunities, and they're saying, well, the first thing we have to do is protect it. So I mentioned before about talking to commercialization people within the university. So within the university, we have a group of people who assist with that, with me then talking to patent lawyers, patent attorneys, to try to protect the intellectual property or the IP of our ideas. So we've been through that process. When we develop that, the next stage is then to try to secure funding to develop the idea. So I have enough funding to do things on a small scale in the laboratory, but we're now at the point where we need to scale up. We need to demonstrate this outside of the laboratory. Things start to get more and more expensive. And this is where having an industry partner, particularly like FFI, as you said before, with deep pockets, can come along and assist that transformation. And that is exactly what's happening. We've created a company. It's called Sparc Hydrogen. They've injected some funds into it, and I can now call on those funds to employ people to develop the technology, and B, also to start building up the scale. So right now we are almost at the point where we're going to be doing a real on-sun demonstration. So that's going to be happening next month. So it's a very, very exciting time. So that's what that money has allowed me to do. It's allowed me to do that transition and also to do it more quickly. It's also allowed me to free up some of my time, so I can spend more time on my research, and that's helping as well.
Very good. Okay, so you've got a month until you actually do this real, life in the field example of what you've been working on. And I've heard on a few other podcasts, you've discussed how this would look a bit like perhaps in the middle of Australia with a big burning sun. Could you elaborate for us, how is this actually going to look like in a month's time?
Yep. Okay. So what we are trying to do, as I said before, is take out the energy from the sun. Now, the energy from the sun, we might think it's very intense, but it's actually very, very dilute, the energy from the sun. So it takes a lot of land area to get a significant amount of energy, especially it takes a lot of energy to split water into hydrogen and oxygen. So typical photovoltaic farms, for example, just have the photovoltaic cells laying out, and if you've driven past, you might have seen one of these big farms with lots of photovoltaic cells all pointing towards the sun, pointing towards the north. Some of the fancy ones track the sun, from morning until dusk. So in a sense, that's similar to what our technology will do. But what we've found is that we can have an advantage by concentrating the sun. So rather than just having what we call one sun coming onto our reactor, we can collect the sun and focus it onto our reactor. So instead of having one sun, we will say, for example, have 50 suns or 100 suns. So that increases the amount of energy coming onto a smaller area. So that has several advantages. One is the size of the reactor that we need to build is smaller. The materials that we're using as the photocatalyst, they do have some precious metals, so it means we're able to limit the amount of metals that we can use there. We find that the material responds very, very nicely to the increased concentration. So if you put on 5 times as much sunlight, we get 5 times as much hydrogen out, so that's good. But what we also find is when you concentrate the light, you also get heat. And we find that increased heat also assists with the chemical transformation as well. So it's got to do with the kinetics of the reaction. So all of these things conspire together in a positive way to give us an enhanced hydrogen output by using concentrated light. So we imagine what this would look like is it would be a collection of mirrors out in the arid desert where we're collecting the sun, focusing it onto a reactor, passing water over it, and at the end, bleeding off hydrogen and oxygen. And then that could then be put into pipes and shipped around the country or shipped offshore to ships where it could then be shipped around the globe.
Wow, that is actually unbelievable. That is so amazing. And, this is happening so quickly. Like, what's been the time frame, actually, if I could ask quickly, from when obviously it's been the culmination of years of your own research, but actually when you started and to here now to having it out in the field?
So our patent was submitted about 2.5 years ago.
So not even that
So
long.
all that's happened so we've gone from that to having an on-sun demonstrator next month in under 3 years.
Unbelievable. That's an testament to your team's work. Congratulations. But thank you so much.
I must acknowledge my team's hard work. It's not just me. Yeah.
Well, thank you so much, Greg, for joining me today. It was really great chatting with you.
Yeah, my pleasure, Chloe.
Thank you for watching. Subscribe to Dynamic Climate Now to stay informed and inspired by the dynamic intersection of climate change and business innovation.